In the last section, we learned how we can evaluate definite integrals using geometry. Now, that is not often convenient. Instead, we have a very powerful theorem called the first fundamental theorem of calculus. There are two fundamental theorems of calculus, and the first one is the most often used one, and that's what we will discuss in this video. A few sections ago, we learned how to find an antiderivative. An antiderivative is just a member of the family of indefinite integrals. And so we use that notation of the indefinite integral, and we didn't really explain why we used that crazy notation. So here we see how the antiderivative is related to the definite integral. If we have a function that's continuous on a closed interval, and we have a function that's the antiderivative of that function, then we can easily evaluate a definite integral by simply taking the antiderivative f and evaluating it at the upper limit of integration, evaluating it at the lower limit of integration, and then subtracting those results. So let's take a look at how this plays out in an example. We have simply an antiderivative. We don't need the whole family, we just need a single. Here we have an integral, a definite integral, of the function 5. And we want to evaluate the definite integral from 4 to 10 of that function. Now, rather than do that geometrically, instead, we can go ahead and apply the fundamental theorem of calculus. So, if we remember from the previous section about how to find an antiderivative, we know that the antiderivative of 5 is going to be 5x plus c. Now, that 5x plus c, that is the whole family of antiderivatives. And if you remember in our theorem, antiderivative. So instead of using the whole family, we can specify the exact antiderivative that is going to be the easiest. And it is easiest to just choose c to be 0. So now we have an antiderivative. And the notation we use to say we want to take this antiderivative and evaluate it at the upper and lower limits of integration is to use a vertical bar, and then our lower limit of integration and our upper limit of integration. And then we will simply take that antiderivative 5x and evaluate it at the upper limit of integration. So I'm going to replace x with 10. And then I will replace the x with 4, the lower limit of integration. And then we simply subtract those results. So we get 50 minus 20, which is 30. Now, because this is the first time we've used the fundamental theorem of calculus to evaluate a definite integral, let's just verify that this corresponds to what we would obtain geometrically. Since this is an easy function to graph, let's go ahead and examine the graph. What is the function that we're graphing? We're graphing the integrand. And the integrand is y equals 5. And so y equals 5 is a horizontal line. And we're looking specifically between 4 and 10 on the x-axis. So here we have the horizontal line y equals 5, and we're looking between x is 4 and x is 10. Where do those values come from? The lower limit and upper limit of integration. So if we look at this function, notice it is non-negative on the interval. And since it's non-negative on the interval, we have the definite integral will correspond to the area under the curve, between the curve and the x-axis, that is, on the interval. So, what is this area? Well, this is a rectangle of height 5 and width 6. So the area is 30, which corresponds to the definite integral's value. The benefit of this method is that the benefit of the method that we just went over at the beginning is that I don't have to graph anything. Now, that's not to say that evaluating a definite integral is always easy, but typically it is easier than graphing the function. So let's take a look at this definite integral. Now, this one would be more difficult to find geometrically. In fact, most individuals aren't aware that there is a formula to determine the area under a parabola, and I venture to say that even if you did know that it existed, it's not necessarily in the forefront of your memory. So let's go ahead and evaluate this using the fundamental theorem of calculus. So this would equal, now let's find an antiderivative of this integrand, 6x squared. So 6x squared, I will raise the exponent on x, and I will divide by that new exponent, plus 2x, I'll raise the exponent on x, I'll divide by that new exponent, minus 3 is a constant, so its antiderivative is going to be 3x. Now, I don't have to worry about the plus c. Why? Because we're not worried about the whole family of antiderivatives. The fundamental theorem says that I just have to use an antiderivative. So now we have multiple terms in our antiderivative, so we're going to group those together, and then we will again put our lower limit of integration and upper limit of integration. Now let's do some simplification. 6x cubed over 3 is just 2x cubed. The 2's cancel in the next term, so we're just left with x squared minus 3 times x from 1 to 7. Now let's evaluate our antiderivative at 7. So we have 2 times 7 cubed plus 7 squared minus 3 times 7. Then we're going to subtract off that antiderivative evaluated at 1. So make sure we put in that grouping symbol, and we're going to subtract all of what follows. So subtracting the 2 times 1 cubed plus 1 squared minus 3 times 1. And now it's just a matter of some arithmetic. So we obtain 686 plus 49 minus 21 minus 2 plus 1 minus 3, which is 714. Now let's look at another example. Again, we're going to find an antiderivative. This time the change up for you is that this variable is t. There's another cool little thing that we can note at the very end of this. But let's go ahead and proceed as normal. So if we go ahead and find an antiderivative, we have t to the 6th over 6 minus 8t squared over 2. And we're going to evaluate this from negative 2 to 2. So let's simplify. We obtain t to the 6th over 6 minus 4t squared evaluated from negative 2 to 2. And so now, substituting our upper limit of integration in, we get 2 to the 6th over 6 minus 4 times 2 squared minus, and now let's subtract off if we put in our lower limit of integration. So we have the 6th power of negative 2 over 6 minus 4 times the square of negative 2. So if we evaluate this, we obtain 0. Now this is interesting because this relates to a property of our graph. if you look back at this original function, f of t, let's just examine that for a moment. F of t equals t to the fifth minus 8t. This is polynomial, so it might be easily seen by you that this is an odd function. We know that because every exponent of t is odd. Now, you also can verify this algebraically by remembering that if I substitute in negative t, then this would be negative t raised to the fifth minus 8 times negative t. And this is going to be negative t to the fifth plus 8t, which is the same thing as negative f of t. So that means that this is an odd function. That's the verification. Now, there is a graphical understanding of what's happening because this is an odd function. Remember that odd functions are symmetric about the origin. So let's take a look at the graph and see what's going on. We obtain a definite integral of 0. This is the graph of the function, and we're looking at the region between the curve and the t-axis, the horizontal axis, on that interval from -2 to 2. So you'll notice that sometimes this function is above the t-axis, sometimes it's below the t-axis. But there's, because of the symmetry, some correspondences. For example, this area and this area are the same, but because those regions are on opposite sides of the axis, while they have the same area, their definite integrals are not the same. They're opposite signs. Same magnitude, but opposite signs. Likewise, if we look at this region and this region, they are the same magnitude, but opposite signs. So whenever we add this area with an opposite sign of this area, they zero out. Likewise, this cancels this out. Therefore, whenever we go back, so let's look at a new integral. Sometimes it becomes beneficial to rewrite our integrand in order to find the antiderivative. That is typically the difficult part of integrating, is finding the antiderivative. So we can rewrite this as the square root of 2 times x to the -1/2 dx, and then apply the power rule. So raise the power on x and divide by that new power. So this is going to be 2 square roots of 2 x to the 1/2 evaluated from 1 to 8. We can tidy that up a little bit more. We have square root of 2 times the square root of x. So we have 2 square roots of 2x. These are both evaluated from 1 to 8. Now, we'll substitute in our upper limit of integration, and then subtract off the value whenever we substitute in our lower limit of integration. So we get 2 square roots of 16 minus 2 square roots of 2, and the square root of 16 is 4, times 2 is 8. So we have 8 minus 2 root 2. Now let's look at a more interesting integrand. 3 minus the absolute value of x minus 4. Now, the absolute value of a function is like a piecewise defined function. So it might be beneficial for us to recall that the absolute value of u is equal to one of two things. it's equal to itself if u is not negative. But if u is negative, we have to change the sign. So if we look at absolute value of x minus 4, this is going to equal one of two things. It will be x minus 4 if x minus 4 isn't negative. Well, x minus 4 isn't negative as long as x is bigger than or equal to 4. Alternatively, if x minus 4 is negative, then we have to change the signs. So x minus 4 is negative if x is less than 4. So therefore, if you look at where this transition takes place, the transition of this portion of the integral changes sign at 4, but our interval is between 2 and 5. So we're going to split this integral up into two integrals. So the integral from 2 to 5 of 3 minus the absolute value of x minus 4 dx equals the definite integral from 2 to 4 of 3 minus the absolute value of x minus 4 dx plus the integral from 4 to 5 of 3 minus the absolute value of x minus 4 dx. Well, from 2 to 4, x is less than 4. If x is bigger than 4, which it is on the interval 4 to 5, then x minus 4 is not negative. So we can simplify these integrals and remove the absolute values. The integral from 2 to 4 of 3, and then we'll subtract off the absolute value of x minus 4. But since x is less than 4, the absolute value of x minus 4 is negative x plus 4. Plus, now, since x is bigger than 4 on the interval from 4 to 5, this is 3 minus x minus 4. Now let's simplify each one of these integrands. This is the integral from 2 to 4 of, that will be x minus 1. Plus the integral from 4 to 5, and this will be negative x plus 7. So now if we integrate x minus 1, I raise the power, divide by the new power. Don't forget the grouping symbols, and this is from 2 to 4. Plus, again, negative x squared over 2 plus 7x now, evaluated from 4 to 5. Substituting the upper and lower limits of integration in each one of these groupings, we obtain 4 squared over 2 minus 4 minus 2 squared over 2 minus 2 plus negative 5 squared over 2 plus 7 times 5 minus negative 4 squared over 2 plus 7 times 4. And this equals 13 halves. Now let's look at an integral that involves trigonometry. Oftentimes our trigonometric identities can help us evaluate an integral, such is the case here. Here we have the integral from 0 to pi over 4. And then notice the numerator is just a version of our Pythagorean theorem that says that sine squared of theta plus cosine squared of theta equals 1. So if I subtract sine squared of theta from both sides, we remember that cosine squared of theta is 1 minus sine squared of theta. So the numerator is just cosine squared of theta. The denominator is unchanged. So we are really just integrating 1 from 0 to pi over 4. Now just a little notational thing. We don't have to write the 1 there. We could just write the integral from 0 to pi over 4 of d theta. And if we do that, it's implicit that the integrand is 1. So if we integrate 1, we obtain x. And this is from 0 to pi over 4. Substituting our upper and lower limits of integration in for x, and we obtain just pi over 4. Now remembering our tricks from just finding antiderivatives, we know that if our denominator is a monomial, or a single term, then we can split up this numerator over that common denominator. Now I want you to notice that if I take this integrand and combine those two fractions, I obtain the original integrand. So this was just cosmetic. And we have the integral from 1 to e of 1 minus 2 over x. Which, if it helps, I can rewrite that as the integral from 1 to e of 1 minus 2 times 1 over x. So the integral of 1 is x minus 2, and then the integral of 1 over x is the natural log of the absolute value of x. And this is going to be evaluated from 1 to e. So substituting in e, I get e minus 2 times the natural log of the absolute value of e minus, now substituting our lower limit of integration, 1 minus 2 times the natural log of the absolute value of 1. So this is e minus 2 times, and the natural log of e is 1, minus the quantity 1 minus 2 times, and the natural log of 1 is 0. So we obtain simply e minus 3. And now for the last example of this video. Here we are going to find the area of the region bounded by the graphs of the equations given here. Anytime you are to find the area of a region, graph the region. Don't just assume that you take a definite integral. You will end up taking a definite integral, but the graph will help you determine what's going on with your limits of integration and your function. So let's take a look at that graph. X cubed plus x is a cubic, and x equals 2 is a vertical line, and y equals 0 is our x-axis. So if we graph that, and it's perfectly acceptable to use a graphing utility like Desmos or your graphing calculator to obtain the graphs here. We're not testing your graphing capabilities. We're testing your calculus capabilities in this instance. So let's take a look at the graph. So here we have the graph of the function. The graph of the function, y equals x cubed plus x, is this curve. Now because this curve lies above the x-axis on the interval from 0 to 2, the definite integral does equal the area of this region. So the area equals the integral of x cubed plus x dx, and then this corresponds to the limits of integration 0 to 2. And so now finding our antiderivative is not difficult here. We have a polynomial, so I raise the power, divide by that new power, raise the power, divide by the new power, from the lower limit to the upper limit. Putting these upper and lower limits in for x, we obtain 2 to the 4th over 4 plus 2 squared over 2 minus 0 to the 4th over 4 plus 0 squared over 2. And this yields for us 6.